All right, it is Friday, January 8th, 2021, chemistry, chemistry CP. We're trying to get through how you name molecules when you are dealing both with polyatomic ions and ionic combinations, as well today as doing covalent combinations of nonmetals. So first, I just want to point out, when we look at the periodic table, the way it's organized, the way it's structured, tells us a lot about how we're going to make arrangements of elements and groups of elements. The entire first column of the periodic table is called the alkali metals. These elements will only combine with other elements if, as part of the deal, they get to give away one electron. Hydrogen, lithium, sodium, potassium, and so forth are all group 1 elements, used to be called group 1A, and they will only engage with other elements if they give away one electron. So there's no doubt about the group 1A elements. They are always going to be a 1 plus charge in every situation. And that would be stuff like hydrogen, lithium, sodium, potassium, ... On the periodic table, every element in the second column, which is named the alkaline earth metals, will only combine with other elements or group of elements on the periodic table if they get what they want, and that is unconditionally that they give away 2 electrons and become a 2 plus charge. So beryllium, magnesium, calcium, ... all the elements in group 2A, there's no question about what kind of charge state they would be in if they're combined with someone else. They're always going to be group 2. They're always going to have an oxidation number of 2 plus. They're always going to be giving away 2 electrons to combine with anyone else. The next column is down here in the transition elements. And now things are not that definite. No, I can't say that this is going to be always a 3 plus and this is always going to be a 4 plus. In fact, this region here can be 1 or 2 or 3 pluses, and some of these elements have multiple choice. Sometimes they're going to be a +2, sometimes they're going to be a +3, sometimes they're going to be a +2, sometimes a +4. They're scattered around, and it's not just this chunk here. It kind of goes up until this diagonal where we are bumping up against the metalloids. So what I can say with certainty is that boron, actually, I'm not even sure I can say this with certainty about boron, but I can say with certainty that aluminum will always choose to be a +3 state whenever it combines with other elements or groups of elements. And directly underneath it, gallium for sure. By the time we get below that, it's less definite. They're more flexible, like these guys here. And for boron, I speculate, without looking it up, without asking Wikipedia or Lord Google, I speculate that boron probably is only a 3 plus state as well, but not entirely sure. A 4 plus state for sure is carbon, and below that, silicon. After that, I would have to look it up on a list. Turns out we have a bunch of handouts that are a list of information like this. Periodic table, always have it there and refer to it. This handout, called List of Common Ions, shows that aluminum is always a 3 plus charge. That's what monatomic means. Only one state that it's going to be in. You should recognize that this 1 plus list here are all the group 1 elements: hydrogen, lithium, sodium, potassium, dot, dot, dot. All the group 2 plus: beryllium, magnesium, calcium, dot, dot, dot. 3 plus: aluminum's the only one written on this particular list. Uh-huh. Another handout called Common Ions Listed by Charge. You have to study this one a little more carefully. Another list entitled Monatomic Ions. That means they only have one charge state they're ever going to be in. Look who's on the list: lithium, sodium, potassium. Again, the alkali metals. Cesium. Well, no, sorry, this is still alkaline. Beryllium, magnesium, calcium, strontium. The group 2 metals, the alkaline earth metals, down to barium. Here's aluminum. Notice that we're skipping the entire transition section of the periodic table. Aluminum, 3 plus. Underneath that, gallium, 3 plus. So aluminum, gallium, yep, I put those on this list here and said they're always going to be a 3 plus. I'm looking. I was hoping that I could see more information about carbon and silicon, and I do not. So I'm starting to, yes, I do see carbon. It's back on this list of common ions, monatomic anions. Carbon is by itself, and so I'm not even sure that I should include silicon on my little notes here. But carbon for sure is, and I listed it as always being a 4 plus. Carbon's always going to be a 4 minus. It's on the other side of the tipping point and wants to gain electrons in order to become a full outermost shell. Here's carbon. Next to carbon, to the right, is nitrogen. Nitrogen is always going to be a 3 minus charge. That's why it's on this page called monatomic ions. Anion means gaining electrons. Nitrogen and phosphorus both made it onto this list, N and P. Here they are on the periodic table: nitrogen, phosphorus. Next to them, to the right, is oxygen. Oxygen and sulfur below it, selenium and telluride. So 1, 2, 3, 4 elements. These are always, without exception, going to be 2 minus charge on them. That's oxygen, sulfur, selenium, and tellurium. To the right of them, the halogens. Everyone in this column is strictly going to want to gain 1 electron as part of making any deal of combining with other elements. So always a 1 minus charge, and you can see the list here: fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine. Ta-da! And I can't even tell you for sure about astatine. These elements are so unstable, they tend to disintegrate before you can do any meaningful reactions with them. And of course, we get to ignore the last column, the noble gases, because they're never going to combine with anyone else. They are happy. They are content. They are at peace with themselves. They have full valence electron shells while they're neutral. Life couldn't be better for these guys. For everyone else, if you are the left 2/3 of the periodic table, you're going to want to give away electrons, and that makes you the cation. The cation is the member who gives away an electron to become positively charged. The elements in the upper right third, sort of diagonal corner of the periodic table, they're only interested in gaining electrons. An atom that has gained electrons is called an anion. And we represent these with negative charges, since electrons are negatively charged. Now, there are all kinds of combinations of elements that we can create, and groups of elements. What your goal is to be able to combine these things and write them as a neutral molecule and write the formula correctly for them. So I'm going to make up a problem and say, suppose I have element Giselle, and Giselle is always a 3+ charge. And I have element Amber, and element Amber is always 2- charge. That should be a superscript to the right. I just didn't write the minus sign far enough to the right. Okay, and so Giselle and Amber are going to get together to create a molecule. I'm going to try to graphically represent Giselle as a column, 3 lines long on my piece of paper, where each row represents a positive charge. So this is Giselle. Amber, I'm going to draw right next to her, is a -2 charge. Now I could go up with positive and down with negative, but I'm going to put these things side by side. So here's Amber with a 2- charge. So if I took one Giselle and paired it with one Amber, it's not going to work. And the reason it doesn't work is because this is not electrically neutral. To be electrically neutral, that means for every positive, there's a matching negative. And in this situation, they don't match. I have one more positive than I have negatives. And I can't, saw off an arm or a leg or something like that. No. But what I can do is clone these people. And so I'm going to clone Amber and duplicate her and say, okay, here's my Amber clone. Of course, just like the original Amber, Amber clone has 2 negative charges. Well, this hasn't made the situation any better. Now I have one more electron, then I have protons. This is no better, or so it appears. But I keep this process up and I say, oh, I'm going to add another Giselle now. And so here comes Giselle's clone. 3 more positive charges. 1, 2, 3. And if you're a cynic, you could say, oh, this is even worse now. Before I was only 1 proton too much. Now I'm 2 protons too much. Mr. Turek, what were you thinking? Stay tuned. Here's what I'm thinking. If I now clone Amber again, ta-da! I achieved my objective. I've used 2 Giselles while I've used 3 Ambers. And when I create this combination of 3 Ambers for every 2 Giselles, I finally have a neutral molecule. For every positive, there's a negative. And this is a stable molecule. Now, here's a shortcut that I'm going to refer to for the rest of your lives. It's crisscross. If I write Giselle as a 3+ cation, and I write Amber as a 2- anion, and always cation first, anion second, positive first, negative second, to work out a neutral molecule, the numbers will always end up being a crisscross. So if I take this 3 from the 3+, and I make it a subscript for the Amber, if I take the 2, not the minus, just the 2 from the 2-, and I crisscross here and make that the subscript for the Giselle, that makes this Giselle 2 amber 3. Ta-da! This matches this diagram. Giselle 2, amber 3. By crisscrossing the magnitudes of the electric charges, I will always end up writing the formula for a neutral molecule. Get it? So when I say crisscross, that's what I'm talking about. Now, let's do an example from the periodic table. I will randomly pick magnesium. Magnesium is always going to be a 2 plus without any questions about it. Now I can go pick some other random anion. Oh, heck. How about, I don't know. Oh, let's do one of these guys. Phosphide. That's not too exciting. But how about phosphate? All right, let's do phosphate. Phosphate is the name of a polyatomic ion that is always a group of 1 phosphorus, 4 oxygens, and this group always gains 3 electrons, so 3 minus electric charge. So I'm going to write that PO4 with a 3 minus charge. Now I want to combine these things and make a neutral molecule. By crisscross, this 2 will go down over there. This 3 will go down over here. And to write this, that would be magnesium, subscript 3. And now I have a question for you from me. What do I do with this 2 if there's a 4 there already? Should I multiply them and make this an 8? No. Should I put the 2 after the 4 so that it looks like 42? No. How about in front of the 4? No. What I need to do is to show that I'm using 2 groups of phosphate polyatomic ions. That means I am obligated to go open parentheses, PO4, close parentheses. The parentheses are saying this is my polyatomic ion group. I can't break it apart. And if I need more than one of them, I better put parentheses around it so that when I bring down this 2 by crisscross, you understand I'm not saying I need 1 phosphorus and 8 oxygens. I'm saying I need 2 groups of phosphate. And I would announce that this is magnesium phosphate to say the name of it. This example has 3 magnesium atoms. It has just 1 I'm sorry, I said that wrong. It has 2 times 1. It has 2 phosphorus atoms in it, and it has 2 times 4 is 8 oxygens in this one molecule. So that's magnesium, 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 phosphorus, phosphorus, 1, 2, 3, 4, 5, 6, 7, 8 oxygen. Woo, as Amber would say. Well, maybe not. But these are all the atoms in this one molecule of magnesium phosphate. And only this is magnesium phosphate because magnesium is always going to be a 2 plus. Phosphate is always going to be a 3 minus. So there's no need for no stinking Roman numerals for a situation like this. The Roman numerals come up when there's the possibility that the cation has different charge states. Everything in column 1 is always 1 plus. Everything in column 2 is always 2 plus. Now, there are a couple other for sure's always doesn't change. Aluminum, always 3 plus. Gallium, always 3 plus. There is a handout. One of these reference sheets is monatomic ions fixed charge. I mentioned here's group 1A elements. Here's group 2A elements. But look, children, here's 2 elements I didn't mention before. What do you think of this? Zinc is always a 2 plus charge, without exception. Silver is always a 1 plus charge, without exception. That's how they ended up on this list entitled fixed charge. That means without exception, it's always going to be that one. Here's zinc on the periodic table. Here's silver on the periodic table. And there's nothing that you would look at as a first year chemistry student that would tell you, oh, obviously zinc is only going to be a 2 plus. No, it's not obvious to you. That's why we have this table, this handout to give you. But wait, let's talk about some of these snarky elements that have multiple choices. That would be the handout entitled cations with multiple charges. Copper, for example. Sometimes it's 1 plus, but sometimes it's 2 plus. And because we don't know which one it is until we build our molecule, we need to express which one it is in writing. And for that, ta-da, we use the Roman numerals. So copper with a 1 plus is copper Roman numeral 1. Copper with a 2 plus is copper Roman numeral 2. This applies for any elements anywhere they appear on the periodic table where it has multiple choices for how many electrons it gives away, always for the cations. Here's a list, and here's what it says. It says copper 1 or copper 2, chromium 2 or chromium 3, iron 2 or iron 3, cobalt 2 or cobalt 3, lead 2 or lead 4. Wow, how about that? That's not two numbers next to each other. One's double the other. Same thing for tin, tin 2 or tin 4. And manganese, manganese 2, manganese 4. But this one, nickel 2 or nickel 3. So don't memorize this list. Have the reference sheet handy anytime that you need to refer to it. Okay, I am going to